So as you may notice that I do the screen recording and I post the video on my course view as well. If you go to my course view and you click on the playlist, you're gonna see the screen recording for the class. It's on the playlist in my course view. So if you click on that one, you're gonna see the recording, which you can watch it later in case that you cannot follow in class. So last time we stopped at the integral test. So the plan for today is we are going to start talking about integral test again, give you 2 more examples, and then we're going to move to P series, and that is the end of this handout. So the exam 1, which is going to be next Wednesday, is up to section 8.4, which is at the end of this handout. So once it come to the end of this handout, we're gonna wrap up everything and get you ready for the exam. Okay, so first of all, we're gonna spend about 30 to 40 minutes talking more about the integral test and P series. So I think we have about half of the class now, about 15 students, which is okay now. So let's go to the theory again. So last time I told you that for the integral test, this is hard to use, so people try to avoid it. But this is a good one that we can relate the series and integral together. So the idea is that if you have a function that you define to be the same thing with a subscript k, and then you can have a relationship that the integral from 1 to infinity gonna be in between the summation from n to n equal to 1 to infinity and summation from n equal to 2 to infinity. And then once you have this relation, you can see that if the integral is convergent, so it's gonna force that the series is convergent as well. And then if the integral is divergent, it's gonna be the case that the series is divergent as well. These two series must be the same because it's only different. The difference is only when the first term n equal to 1 and n equal to 2 here. So the convergent and divergent pattern must be the same for this one. Once you figure out the convergent and divergent for integral, you can just conclude the divergent and convergent for the series as well. So the theory looks super hard to understand, but actually the proof is not that easy. But for calculus class, we're gonna just pick up the result and use it. So if you are interested in the proof, you can look at the book, but that is not the content for the class. For this class, we are going to just say that when you see the function that you feel like you can integrate it, you can apply the integral test and conclude the divergent and convergent by take the integral and then compute it. So let's take a look at example. So last time we said that in order to use the integral test, you need to check that the function is continuous, positive, and decreasing. And then you compute the improper integral here. And then after that, if you get a limit L, you say that it is convergent. If you get the limit it's plus or minus infinity, you're gonna say that it is divergent. Basically, continuous, you don't have to check it because most functions, they are continuous. So positive, it's easy to check, and decreasing, sometimes it is easy to check, you can skip it. But if you see the function that is not easy to see that it is decreasing, you probably need to show it by differentiate one time. So last time we do the integral test here, and then we have summation from k start from 1 to infinity, k over k squared plus 1. So I'm trying to do the integral test. So I let fx to be the same function here. I just switch k to x, and then I say that it is obvious that f is continuous, of course, because there is no 0 on the denominator. So the denominator cannot be 0, so always continuous. And then always positive because everything is positive here. And then for decreasing, I say that, yeah, if I differentiate one time, the function less than 0, so which means the function is decreasing. So I check all the condition here. and then after that I integrate fx start from 1 to infinity, so I get infinity, so it means that the series is divergent. So we're gonna redo this type of question, 2 more questions, so to get you to be familiar with the integral test more. Okay, let's do it. Part B here we have summation start from k equal to 0 to infinity 1 over k squared plus 4. Think of the technique we learned in class. So we have telescopic series, we have geometric series. But you can see that this type of question, you cannot use geometric series or you cannot use telescopic series at all, because if you want to use telescopic series that we learned last week, you probably need to see the minus sign. But there is no minus sign here. Looks like you cannot do telescope, and this is not the geometric series as well, because you have k squared plus 4, not the pattern of geometric series. But this function you can integrate it, so we're gonna apply the integral test. So let's do it. So we're gonna start by let fx equal to 1 over x squared plus 4. This is the function that I just copy from the question, just switch k to x. And then because we're gonna start at x equal to equal to 0 to infinity, so we're gonna copy it, so it should be x greater than or equal to 0. Does it make sense? This is because we just copy everything from the series. And then before applying the integral test, we're gonna check the condition first. So we have to check some conditions. So condition number 1, it is continuous. So you can say it is obvious that it is continuous. It is clear because the function is 1 over x squared plus 4. That's no way that you're gonna get 0 on the denominator. So the function is continuous. Is the function positive? It is always positive. You can think that if you plug in x greater than 0 here, it's gonna be x squared greater than 0 always, and then plus 4 greater than 0. So this is clear that it's gonna be positive. So it is clear. And clear, so positive is clear. And then is it clear that the function is decreasing? Well, if it is not clear to you, you can take a differentiate one time and show me that it is less than 0. But here the function is easy enough, because you can imagine that if you compare 1 over x squared plus 4 and 1 over x plus 1 square plus 4, right? It's like, this is just, let's say the series one. If you compare the series using the term n and n plus 1, doesn't have to be x. If you compare the series, the term n and n plus 1, which one is bigger? You can see that the left hand side is bigger, right? Because the denominator is not heavy compared to the right hand side. So this one gonna be, is that clear? Like 1 over 2 gonna be always bigger than 1/3 or something like that. So because n squared plus 4 always less than n plus 1 squared plus 4. So this thing gonna be okay to say that the function is decreasing. Pretty clear actually, because the previous term must be bigger than the next term, because it is like you just add more numbers in the denominator, so the function gonna be smaller and smaller. Does it make sense? So once you check these 3 conditions, and then yes, it's fine now, so you can use the integral test. So what would you do for the integral test? So we're gonna integrate 1 over x squared plus 4 dx, start from 0 to infinity. Okay. And then if you integrate this one and then you get the answer, one number that is not plus or minus infinity, you're gonna say that this is convergent. But if you get plus or minus infinity, you're gonna say it is divergent. So let's integrate this one. So it's gonna be limit, the problem is at infinity, right? So we're gonna do 0 to t, and then t go to infinity 1 over x squared plus 4. First of all, you need to know how to integrate 1 over x squared plus 4. It's a long time ago from calculus 1, but let me give you the formula. So in calculus 1, we learned that this is a formula that, it's my fault that I never let you memorize the formula, but this is 1 over x squared plus 1 dx. Usually this one, this is arctan x plus c, right? But if you see integrate 1 over x squared plus a squared dx, if it is something like you have something more, not just 1, you have the constant a squared, the formula gonna be 1 over a arctan x over a plus c. Well, if you need this formula, I will give you on the exam, but keep in mind that you can prove it. If you want to do it by yourself, you can do u substitution. Just, pull out a square and then do u substitution. You're going to get the same answer with me. But this is calculus 2. We are not going to test you on integration technique because we believe that you already passed calculus 1. And then if you take time, you can do it. But, this is not the content for calculus 2, so the formula going to be given. So here, you can integrate that one. And then you're gonna get limit t go to infinity. So you integrate this thing, you're gonna get 1 over 2 arctan x over 2. For those of you who cannot follow, imagine that 4 is 2 square. 4 is 2 square here. And then if you apply the formula that I put in the box, so you're gonna get that one. And then you plug in 0 to t. Okay. X start from 0 to x equal to t. Okay. Well, the function that I will put on the exam or on the homework anyway. So this type of function gonna be the one that you can integrate it. If you cannot integrate it, I will give you the formula. So you're not supposed to do hard work on integration here. So it's gonna be the one that's super easy that you can do with the u substitution, or it's come with the formula. And then now you just integrate. You already integrate, so you're trying to compute the limit here. So you're gonna get 1/2 arctan t over 2, and then minus 1/2 arctan 0. Okay, so I plug in t and 0 over there, and then arctan 0, this is 0, right? Because tan 0 is 0, so arctan 0 is 0. So the second term gonna be disappear, and then you only have 1/2 times arctan t over 2. So what is the limit of arctan t where t go to infinity? So we just keep talking since last week that if you have the function fx equal to arctan x, this is a function that you cannot forget because the limit, I always tell you to memorize this one. So the limit is going to be pi over 2. 1x go to infinity, limit is going to be pi over 2. Which means arctan t over 2 here, when you take limit t go to infinity, it's gonna go to pi over 2. Because this is the property of arctan x. It's gonna go to pi over 2 and multiply with 1/2 over there. So the answer is gonna be pi over 4. Which is convergent, right? So the improper integral here is convergent. That means you can conclude now that the series 1 over k squared plus 4, k start from 0 to infinity, this is convergent as well by the integral test. By the integral test. Does it make sense? So when you use the integral test, you can see that it is not easy to use because you have to integrate it. But it is a good to know, but not easy to use because you have to integrate it. Anyways, some students have a hard time to understand, and you cannot make more conclusion from the integral test. Some of you are gonna say, Ajahn, can we conclude that it is convergent and the series, when you sum it, the summation gonna be pi over 4? No, you cannot. You cannot make further conclusion at all. So once you have this one, this is convergent, so the series is convergent as well, but you do not know the limit. Note that. Note that you cannot conclude that summation 1 over k squared plus 4 k start from 0 to infinity equal to pi over 4. You cannot. The integral test is not the tools that you can make a conclusion about the summation. You only know that it's going to be convergent or divergent, but you do not know the limit. The theory doesn't give you the limit. So you just know that it is convergent because the improper integral is convergent. Okay. Alright, we're gonna do one more example on this one. So hopefully you feel much more comfortable with the integral test. This is supposed to be the hardest question on the exam one for the integral test because you have to use so many things. Alright, so let's do the next part. So if you are not well, I mean, I will post the note after class, so you don't have to jot down everything right now. I mean, if you do not want to, you can just skip it and then copy the note later. So the next question is summation k log k equal to 2 to infinity. Okay, I think this is the last one for the integral test. Okay, so let's try to do the integral test one more time. So you can see that this is not geometric series. This is not telescopic series. So basically, but you can integrate it if you pick the u substitution to be log x. It's gonna cancel out with this, and then you can integrate it. So basically, we're gonna start the same thing. So let fx is 1 over x log x. This is where x greater than or equal to 2. For the integral test, you start like that. And then now I will just do it pretty quick. It is obvious that f is continuous, right? Because there's no hole on the denominator because you have x log x now. No way that this thing gonna be 0, right? Because x greater than 2. When you plug in 2, 3, 4, and so on, no way that is gonna be 0. It's gonna be some number that is not equal to 0. So it is continuous for sure. It is positive for sure because the logarithm here, the function, one it pass because log 1 is 0, one is part 1, so the function gonna be on the positive side. So which means log x gonna be positive as well, x gonna be positive as well. So clear that it is positive. And also, it is also clear that it is decreasing. Because when the function have 1 over something here, so if you apply n bigger x or bigger n, so the bottom gonna be more heavy, and that means the function is going to be getting smaller, 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 so the function is decreasing for sure. So when you see the function like this, okay to just say that it is decreasing. You don't have to show me f prime x. Doesn't make sense. But like last question, this one decreasing, clear. But the previous question, this one, actually it is clear. But sometimes it is like you don't know which one gonna go heavier, so you can just take a derivative here if you want to. All right, so once you claim that the function is continuous, positive, and decreasing, you can apply the integral test. Now, let's integrate 2 to infinity 1 over x log x dx. This one no formula for you, but you can do u substitution. So integrate 2 to infinity. Okay, let's do the limit first. So you switch infinity to t, and then you take limit t go to infinity. And then now to integrate this one, you're gonna do 1. Okay, let's do it on the side. What is the integrate 1 over x log x dx? So of course it should be integrate 1 over x log x, and then you pick u to be log x, right? And then you get 1 over x here, because this is similar to the thing that we learned in Cal 1, that we pick u to be log x. So this can cancel out. And then now you have 1 over log x d log x. So when you get the thing, you should get log x. plus C, right? Agree? This should be that one. And then this, when you integrate that thing, okay, you can now, okay, let's see. I'm gonna go a little bit slower. So 1 over x log x dx. So I change infinity to t first, and then now I integrate it. So it's gonna be limit t go to infinity. Here you're gonna get log x, right? But you plug in t and 2. Can I do like a little bit quicker here? So I get log x, but I plug in t and then I plug in 2. So I get that one. And then this is just the constant. This part, log 2, this is a constant. I don't care it because when you take limit, it doesn't give you any, you know, like the constant here when you compare to infinity, it's just gonna be just only small number. So it does not affect the convergent and divergent pattern at all. So this one, when t go to infinity, this thing gonna go to infinity as well. Because log t, like when t go big, log t gonna go big, and then of course log big is going to be big as well. So this should be infinity. So then we can conclude that this is divergent. The improper integral here is divergent, which means when you make a conclusion, so you can come back to the series. That series is also divergent by the divergent, sorry, not by the divergent test, by the integral test. Okay. All right, and that is the end of the example of the integral test. With the integral test, you're gonna have one more tools to use it, because integral test can always apply with 1 over x to the p, right? So this function is easy to integrate. Another one is 1 over k to the p. This is also easy to integrate. If you see 1 over k square, 1 over k to the 4th power, 1 over k to the 4th power, like we're gonna just make the formula for 1 over k to the something. We can do it. I mean, if you apply the integral test to that one, the result is on the next slide. It's gonna call p series. Okay. You done with this slide? Good. Okay, next. All right, last content before the break here. So we're gonna have the p series. So if you use the integral test applied to this series, so the series gonna be convergent when p greater than 1. It's gonna be divergent when p less than or equal to 1. You can just memorize this one. It is so handy and easy to use. For example, everyone, for example, summation of 1 over k here. This is p equal to 1. So this is divergent. Summation 1 over k square here. Because k, the power of k is 2. So this is convergent. P greater than 1. Sum 1 over k to the 4th power. This is convergent because k greater than 1. The power of k greater than 1, sorry. And for example, sum of 1 over k to the 1/2. This is divergent because the power of k is less than 1. So this type of series is called the p series. So when you see 1 over k to the something, if k bigger than the power bigger than 1, sorry, the power bigger than 1, it's gonna be convergent. The power less than or equal to 1 is gonna be divergent. You can prove it by using the integral test, but to save the time, we are not going to do the integral test all the time. We're gonna just use this result and call it as a p series. So when you take a look at the example 13 here. So question A here, you have summation start from 1 to infinity, k to the negative 3, this is 1 over k cubed, right? This is convergent by p series. You can say like p equal to 3 and then you get full credit. You just say that. If you have p series, you can say convergent or divergent, p equal to something, and then you're done. So part B, you have summation k start from 1 to infinity. This time it is 1 over k to the 3 over 4. Right? Because that one, that is the k cube, and then take the fourth root. So it's gonna be 3 over 4 here. This one, it's gonna be divergent. How do you know that it is divergent? Because this is p series. P equal to 3 over 4. Every time when you see 1 over k to the something, you can take a look at p. If p is the number that is bigger than 1, convergent, otherwise divergent. So the last one, how about 1 over k minus 1 square here? K start from 4 to infinity. This look odd because this is not like k, but you can switch it. It is the same thing with if you want to be 1 over k square. So the first term here is like, you can see that here start from 4, right? It's gonna, the first term gonna be 1 over 3 square. So you can shift the index k minus 1 over there. You shift it start from k to 3. Does it make sense? So it's gonna be the same thing because you just shift from 4 and then you start to 3, and then you change k minus 1 to k. And this is actually convergent by the p series. P equal to 2. Okay. And that is the end of this handout at page 44. P series, the one that you can conclude the divergent and convergent pattern easily by looking at the value of P here. So before I give you a little break, 5-minute break, so we're gonna just take a look at things you need to know for the exam 1. So next week we're gonna have exam 1 on Wednesday here. So basically it's gonna be the content from the first day up to this handout, so up to P series. So the first lecture up to P series, which means this is going to be all homework 1. So you have to submit homework 1 by can everyone do by this Wednesday? No, yeah, I will just extend it to Friday then. So I'll extend it to Friday. So you can do it. You have 2 more days to do it. But I mean, it's good for you because once I extend it to Friday, so you have more time to do it. But make sure you study on it as well, because next week we're gonna have the exam. So the content for the exam gonna be, first one, improper integral. So we're gonna have more, but this is just the only part 1. So improper integral here, this is going to be, you have 2 types, type 1 and type 2. So the type 1 gonna be the one that you integrate and then you have negative infinity or plus infinity here. That is called type 1. The way that you're gonna fix it, you change it to t and take limit. Type 2 is when you have the problem A and B, but you have the problem because it's gonna make the function is undefined, right? The function is undefined at A or B. So So if the function is undefined at a or b, so it's called improper integral type 2. You can take limit to that one that you have the problem, and then you just compute the integral and then answer the it is convergent or divergent. That is the improper integral one. And the content number 2 that gonna be on the exam is the sequence. Everyone should know how to find the limit of the sequence. So the limit of the sequence, it means you take the limit of a subscript n. Once you take limit of a subscript n here, so it could be two cases, L or plus or minus infinity. Of course, L is convergent and plus or minus infinity is divergent. Make sure that you remember the technique that I told you in class. So the technique that when you do the factoring, when you adjust by using the conjugate, and then you do the L'Hopital rule. So the one that gonna be the problem for you, maybe it is gonna be the L'Hopital rule, because we don't learn the L'Hopital rule in calculus 1 a lot. So that means it's gonna be the new content for you. So you have to be able to apply the L'Hopital rule when you see 0 over 0 or infinity over infinity, or even if you see something like 1 to the infinity, or infinity to the 0 or 0 to the 0, you should be able to apply the take limit and then take log first and then take limit and then do the L'Hopital rule. So this is basically if you take a look at all the examples that we have in class, it should be good, because it could be the case that you're gonna see squeezing theorem, or it could be the case that you're gonna see something like you have to divide everything by the highest power. So the technique that we learn in class could be on this one sequence. And the last one is the checking the series, right? The convergent of the series, convergent or divergent of the series, the thing that we already learned, it's gonna be the telescopic series, the geometric series, and then we also learn the integral test or divergent test first. Divergent test, integral test, and P series. That is the all the content. So I mean, if you follow the handout, you should be good for the exam 1. This is 15% of your grade. I would say that this should be about 5% here for the sequence. This should be about 4%. This should be about 6%. If you feel like it. So it's total 15%. I have not written the exam yet, but it's gonna be okay. So of course this is going to be a little bit hard for some of you, but let's see how it's go. Shall we take a little break here? Yes. So we're gonna just do a little break and then you come back at 11:15. Okay? And well, we're gonna start the lecture again at 11:15. So we're gonna start section 8.5. Once we come back 11:15, we're gonna learn maybe half an hour more. So you can go on 11:50. Okay. So let's do a break and then come for 7 minutes. Come back at 11:15, everyone.